once again, we're going to be talking about Hamiltonian systems and billiards today. These are sort of a broad class of examples that sort of carry all the fundamental notions that we're going to need. But today I'm mostly going to be commenting on the notion of structure in each of these systems and how we can use that structure to get a better understanding of what's going on. Okay. So I'm going to start incredibly basic. The most simple dynamical system you've probably ever seen, which is the simple harmonic oscillator. I almost feel like it's a meme how often we talk about this thing, but it really is sort of like a foundational example in this field, and so I think it's worth talking about. So, just as a reminder, for anyone unfamiliar, simple harmonic oscillator is just something that follows this second-order differential equation. The physical example, what it is that I have some spring hooked onto a mass, and then it bobs back and forth, right? So this is the simple harmonic oscillator. And the standard trick that we teach everyone in like your first course on ODEs is that if you want to understand a second-order linear differential equation, how do you go about doing that? Well, you go about defining a new variable, v equals x dot. V equals x dot, the standard little trick we say, and then v dot equals negative kx. And if we imagine this as a dynamical system in terms of these two variables, the trajectories in this space with x and v just form these perfect concentric circles or ellipsoids or anything like that. Okay, so this is just a nice simple flow in this two-dimensional space where we extend to include this auxiliary variable v. Okay, and we can do all the standard tricks here, right? I can declare a new Poincare section. There's lots of great choices for that Poincare section, and then I can ask the stability map there. And one of the things you'll notice if you do this calculation is that you'll end up with a marginal stability within the Poincare section. And that's just commenting on the fact that this motion is very regular, and if I take a little block along, it just rotates through phase space and doesn't change at all transverse to the flow. Okay. So what's happening? Well, what's happening is, we see this marginal eigenvalue in the stability. It's corresponding to a conserved structure. And this is deeply related to the notion of a symmetry by Noether's theorem. So I won't go into that too much. We'll talk about that more later. Okay, and what is actually conserved here? Well, in every introductory physics course, in either your high school physics course or your quantum mechanics course, you learned that the simple harmonic oscillator had a conserved energy, and that conserved energy in this case would have just been v squared over 2 plus k x squared over 2. Okay. And this is a function of both x and v, and we're going to call it the Hamiltonian. Okay, so this is energy. We can actually rewrite our equations of motion in terms of this. So we can say x dot is dh dv, and v dot is negative dh dx. Okay. So flowing along these directions, we have this conserved quantity given by the Hamiltonian. In fact, the Hamiltonian gives us our equations of motion. One other thing I want to sort of point out in relationship to Hamiltonian mechanics is that this, when written in a matrix form, is exactly the same thing as this right here. So we have this skew symmetric matrix right here which is governing the flow. And in fact, what we can see is that if you want to consider dH dx, dH dV dotted with x dot v dot, what is this? This is the same thing as dH dt, right? How that energy is evolving along the flow. This is the same thing as dH dx, dH dV, 0, 1, negative 1, 0, and dH dx, dH dV. So the conservation of energy is really related to this structure right here. The fact that we have this skew symmetric structure on the vectors in our space, really it's related to, well, it's a two form, if you're familiar with this language. It's a non-degenerate two form, closed non-degenerate two form. And this we're going to call the symplectic structure. Really, it's the fact that we have this at every point in phase space. We have little copies of this skew symmetric matrix that act on all our forms, and as you translate between the different forms, we have some sort of global notion. Okay, so I'm saying it's that matrix, but really it's a copy of that matrix at every point in space. Okay. If you're more familiar with sort of the abstract notion, that may seem a little bit strange, but in fact, Darboux theorem tells us that every symplectic form is locally just this. Every symplectic form is locally just this skew symmetric identity. As you go up in dimensions, does one get replaced by identity matrix, but it's all the same thing. And then we can consider special things. So if we consider what diffeomorphisms can conserve this Hamiltonian, conserve this Hamiltonian and its related structure, symplectic form, we get the class of canonical transformations. And in matrix notation, what is that? Well, it's a Jacobian such that apply it as a change of basis at every point. So these canonical transformations are really just like coordinate changes which conserve this sort of symplectic structure of our space. Especially any physicists feel like this is too elementary. I just want to make sure that we're all comfortable with these structures because many people may have not seen these before. Why do we care? This is going to be a side rant. This doesn't necessarily have to do much with the course, but I think it's a super important thing. If we're all practitioners and we want to go out and solve problems, you know, one of the takeaways from this course is that if you have a symmetry, you must use it. And so I want to point out some things where this can be useful. So there are direct energy conservation methods, where you have some numerical scheme, and at every step in that scheme, you exactly preserve this Hamiltonian, right? So numerical scheme preserves the Hamiltonian. And there's a related class known as symplectic integrators, where the numerical scheme that you use is a canonical transformation. And actually proving that a numerical scheme is a canonical transformation is a lot easier than it sounds. Darboux's theorem really is like an incredibly powerful resource that we have, so we can prove some remarkably strong statements. That's enough about Hamiltonian systems.
I had a quick question about symplectic integrators, just how we define them.
Yeah.
Does it have to conserve the symplectic structure identically, or just up to the order of our integrator?
No, so when you construct these symplectic integrators, they conserve it exactly.
Thanks.
Which, again, it's not clear that that's an easy thing to do, but it is actually possible. And in fact, it's once you get the formalism down, it's a 2-line calculation to show that these things conserve it exactly. Numerical schemes which conserve the Hamiltonian exactly are great if that's the only structure you care about. But it turns out that this symplectic structure actually encodes quite a few more things other than just the conservation of this energy. So in particular, there's a theorem, Louisvilles theorem, which states that Hamiltonian flows preserve Lebesgue measure. And how can you see this? Well, it's actually a 2-line calculation. So x dot is equal to dh dv, and v dot is equal to negative dh dx. So the divergence of the vector field is just d squared h dx dv minus d squared h dv dx is equal to 0. So Hamiltonian flows preserve Lebesgue, and if you do a direct energy conservation, you will preserve the energy, but you may not preserve Lebesgue measure. Whereas symplectic integrators don't exactly conserve energy, but by conserving this symplectic form, you in fact actually do exactly conserve Lebesgue measure, and so you end up getting quite a few more invariants that are related to the symplectic form known as the Poincare invariants for free. So it seems like if you want to conserve the energy, you would want to conserve the energy, but somehow this symplectic form is giving you something deeper about your problem. There's actually a duality between energy conservation and something called action minimization. So this side are the variational people. This side is in some sense the geometric people. And it turns out that at least locally, there's a bijective map between these two, or there is a map between these two. And I always get this wrong, but I think this is the Lagrange transform. In classical mechanics, you may have seen it as something like if your energy is your kinetic plus your potential, your action is your kinetic minus your potential. And you can give that transformation formally even when you can't write it as these kinetic and potential parts. So this is quite a bit of structure that we can sort of rely on both for the analysis of our problem. Right? When we're looking at this Poincare section, we see quite a few marginal eigenvalues that we can't explain. And in fact, you know, in terms of our stability analysis, the marginal eigenvalue is inconclusive. We can't say anything. We can only say that at linear order, it's stable, but we can't say more than that. So these Hamiltonians give us extra structure to help address that discrepancy. We can help understand what is the true stability by looking at these globally conserved structures.